some of this stuff. We talked a little bit about distance. Today we're going to talk about displacement more than anything else, okay? So, the difference between distance and displacement. We're really only going to concern ourselves with displacement, okay? This is how far something is moved directionally from where it started. I'm sorry, I'm supposed to write better this year. I'm going to do a better job on the next thing I write, okay? I promise. Okay? I want it to be legible.
Are you sure?
No. Maybe the next thing, but probably not the next thing after that, okay? I can do it for like one time. Okay? Now, notice. Here is where Vivi, is that what you want to be called?
V.
Vivi.
Yeah.
Is that what you want to be called? No, I'm gonna go V. V lives here. What a great kid. Look at her. Do you have bank? No, you can have a swoopy-doopy.
I have a swoopy.
I always have to have a muse every year. Somebody to draw on all my pictures. Later on, she'll be jumping off a building, flying a truck, whatever. It doesn't matter. Now, her boyfriend lives over yonder. Apparently, she's dating a little short fella with floopy hair, whatever. Now, does he? Nice. Well, it's hot. I mean, why wouldn't you? Now, clearly, she 3 blocks this way, 2 blocks this way. She will tell you that she walked 5 blocks. Right? She walked 5 blocks. You see this? This is not displacement, friends. This is distance. In fact, V just walked, wait for it, the square root of 13 blocks. You see, this is her displacement. See, I've already broken my promise to myself. I was going to write prettier. Okay. She went 5 blocks in distance. All right? Literally, here's Alex's house. If she had gone this route, she would have walked right through Alex's house. Which is fine if the doors line up. Otherwise, it's a little weird. Okay? Like she just walks right through the wall. I guess if you're a Terminator or something or whatever. But here comes B again. All right? But again, the difference between displacement and distance. Distance is how far you've actually moved versus displacement is in a direction. Okay? This is how far we've gone from where we started to where we ended up over here. That's the only thing. Distance will always be greater than or equal to displacement. When would they be the same? If you moved in a straight line, exactly right. If they moved in a straight line, it's potato, vodka. Which is why, back when you're like a little kid and you're doing distance equals rate times time or something, and you didn't even think about it. It's like, oh, rate, speed, velocity, it's all the same. Well, it is in a straight line. Okay? But if you're going in a curved fashion anywhere, if you're doing any other of things like this nature, if you're like flying like this. Oh, last night. Okay. I root for the Giants. It's sad though. This year they are pathetic. But last night I saw the score was 3-2. I'm like, should I turn it on and watch or should I not? I don't know. So I turn it in, and as soon as I turn it on, the scoreboard changes to 3-3. And this guy, Trevor Story for the Rockies, is high-fiving everybody. I'm like, yeah, so they just hit a home run. Great. And then they show the replay. The guy hit it 505 feet. He hit it out of the stadium, for God's sakes. All right? I mean, he got all of it. Last night he hit 3 home runs. All of them were well in excess of 400 feet. Okay? He did not get any cheapies that just barely got out. They were just crushed. Okay? So when they said that guy hit it 505 feet, it went 505 feet to where it hit the ground. Yes? Did it actually travel farther than 505 feet along the arc? Yeah. In calculus and pre-calculus, we talk about this being the arc length up here. The arc length. We talk about this being the straight line distance down here. When they say it went 505 feet, they mean in a straight line. In fact, along the arc length, the distance is quite a bit more than 505 feet. Okay? And that thing was just a moonshot. Oh, Man, he tattooed that thing. But then I didn't realize the reason they had 2 points before was because he hit one earlier that was 459, which he fell on his butt. He hit it so hard. He fell around and landed on the plate. And then he gets up and trots around the bases. And then later, did it not print?
No, it did, but Mr. Reed had 60 packets in front of me, so I harassed him today.
Okay. So in the future, if no one's there, okay, what you can do is you can push on the home tab, and then you can check job status, and then you can change job priority. So
Well,
you
his
click
TA was
online.
sitting there
Oh.
waiting for his, so I just harassed him the whole time.
Hey, hang on. Would you run out to my car
Yeah, where's that?
by the shop? It's like me and my Bronco, right?
I think so.
It's right in my Bronco. Like if you're heading toward the shop, you'll see it. It's not in the shop parking lot. It's just like straight past the shop, kind of. You'll see it.
Past it.
Okay, so here's the way you walk out there and you turn into the shop, right?
Okay.
But just beyond that, you'll see it right in front of you, right in my Bronco. Can't miss
Okay.
it. So I get you in, okay?
What do you need?
In the middle console, there's my allergy pills. They're pink.
Pink? Got it.
Yeah, they should be toward the back of the console, toward the driver's side. Okay, I just need one. Just need one. Okay? Now, anyway, later in the game, I checked. We're like down by 1 million points at this point. Whatever. Oh, look, who hit another one? Yeah, ridiculous. Now, again, arc length, this idea of tracing along here, this distance, that's distance. This is the ball's displacement from where it started from. Okay? The only time they will ever be the same is if you're moving in a straight line. Okay? Now, clearly tonight when you go home, here is, yeah, there you go. I'm sorry, girl. You're going to be, from now on, you're going to be like my muse. A few years ago, it was your sister. Cambria did everything. Okay? Literally every day. It was like, what is our intrepid explorer doing today? And it was easy to draw Cambria because she's very short. It's just very nice.
Yeah.
No, you have that floopy hair. It's easy to draw. Yeah. Anyway, she goes home tonight and she throws her iPhone 12 PRQ5W back on the nightstand, right where she picked it up this morning. This little displacement of this little iPhone is 0 for the course of the day, yes? Nice. One time when I was in college, before Al Gore invented the internet, before we had such cool things as the internet, I'd gone home for the weekend. It was 5 hours from my college back home. Drove home, had a good weekend. Typed a paper. Back in the day, we didn't really have computers as such. I had this kind of a hybrid typewriter / word processor. It was pretty cool. You could see about 10 lines of your paper at a time. It was all saved, and you could actually copy and paste crap. And it was good. It wasn't computer good, but it was a lot better than typewriter. Okay, I missed out on most of the typewriters, fortunately. Okay. So I typed this paper, and there was this little itty-bitty, I guess you'd call it a disk of a thing, where my paper was on. I left it at home. I drove all the way back to college. I get up Monday morning and went, you've got to be kidding me. So I couldn't go, hey, Dad, can you just email it to me? Because there wasn't. So I get in the car, I drive 5 hours back home, I wheel in the parking in the lot just as he's coming in for lunch. He's like, what are you doing? I'm like, I thought I'd come eat lunch with you. And he goes, really? I'm like, no, you dingbat. I'm getting this disc. I turn around and I drive all the way home. 600 miles, 10 hours, total displacement, 0. Now the car, my wallet, although gas was a lot cheaper back then, my brain from having to drive 600 miles in 10 hours, we were shot, all right? But you go out in the parking lot, you're like, geez, his car is exactly where it left off, okay? Mr. Groom, you were gone for like 10 hours, that's right. What was your average velocity? That's a good question. So what we're going to talk about is, of course, we're going to talk always in this class about displacement, okay? Once in a while, someone will say, they will slip up and use the word distance when they mean displacement. I will try to correct them gently at first, and then I'll get mean, okay? But then we're going to talk about velocity. Now, I just told you I went 600 miles in, let's just say 10 hours, because let's keep it legal. I don't remember how long it took, but it's something like that. It's about 5 hours, and it's about 600 miles. You have to slow down for part of it, whatever. Yeah, whatever. So what was my average velocity? What would my velocity have been? Somebody say it. Say it.
60 miles an hour.
60 miles per hour. And I'm going to say that, well, you're kind of right, sort of, but not quite. Okay? This is my speed, yes? Because we need to define velocity. Velocity is a change in displacement over time. My total displacement was what? What was my total displacement? 0. 0 divided by 10 is still 0. Okay? So my average velocity was 0. My average speed, however, this is my speed. My average speed was 60 miles per hour. You find them okay? I gave you good direction.
Yeah, they were right where you said.
Thank you. Seriously, they're allergy pills, okay? They're pink. They're not anything weird. That'll help, okay? So the difference between speed and velocity, okay? So keep that in mind as we're doing these things. Now, let's go back and watch B go to her boyfriend's house. I forget how far is it? 3 and 2, is that right? Blocks. What's a block, Mr. Graham? I don't really care. It's not, I don't care. See, I've already broken mine. I'm not going to try anymore. I'm done. I'm done. I don't care. Now, so she walked 5 blocks in 10 minutes. 5 blocks in 10 minutes. You're kind of slow. Apparently you don't like him that much. Okay? So her average speed is 5 blocks in 10 minutes. Or if you prefer, which I do, 0.5 blocks per minute. God, you must be just crawling. The guy must be a thrill to be around. I'm going to go see him. All right. Now, actual distance we said was square root of 13, which is about, what, 3.5-ish? So she was actually going like 3.5 blocks in 10 minutes. This is actually slower, isn't it? Yes? So she's actually, her average velocity is 0.35 blocks per minute. This is her velocity. We'd say this is her actual speed over here. Okay? Now keep that in mind. We will harp on that quite a bit. Wow, we will harp on that a lot. By the way, that one home run he hit last night, 112 miles an hour coming off his bat. Man, that thing got out in a hurry. It was majestic. Even if you don't like baseball, it was majestic to watch. Yeah. Can you imagine that? You're walking through the parking lot, and like all of a sudden a baseball just lands in the parking lot. I mean, it's not like it's a Little League field. Somebody hits up a Little League field. It's a big stadium. Yeah. But that'd have been kind of fun if you got the ball. You could like, this dent came from Trevor Story's home run. Yeah. Or yeah, windshield. Yeah, whatever. Nice. And so, acceleration. What would acceleration be then? Well, it's a change in velocity over time. Okay? Change in velocity over time. Wait a minute. Velocity, we said, was, velocity is speed. It can be thought of this way, speed in a direction. Right? That's another way to think of velocity, is speed in a direction. So if you're changing someone's velocity, what could you be doing? Well, you could be speeding them up or slowing them down, yes? You could be changing their speed, or you could be changing their direction. Right? Something that I always tell kids about is this. People always say things like this. You have the accelerator pedal in your car. Accelerator pedal. The gas pedal, right? The go fast pedal, if you will. But you also have the brake pedal, yes? So that's also an accelerator pedal. Perhaps you want to say decelerator, but I'm fine with that. You also have a steering wheel, yes? Steering wheel also changes your velocity. Later on in chapter 6, we will start going around corners, which things get fun when you go around corners, yes? And it gets kind of exciting. You will be undergoing acceleration going around the corner, yes? Because you were going this way, and now you're going this way, and now you're going this way, and now you're going this way, and hey, we're back around the corner again, okay? We will be doing that a ton. And so we're going to keep these things in mind. Everything we do in this class, math-wise, we will assume constant acceleration. This is a big deal. Everything in this class, we will assume constant acceleration that we do mathematically. Now, we will look at some things that are not constant acceleration. Okay, we will actually videotape them and go, that's clearly not constant, Mr. Groom. I know. Then can we do the math? Ooh, if we had calculus, we could. But with algebra, we have to assume constant rates of change. That's how algebra works, right? So algebra says, hey, if everything's constant, then we can show that this is where it should be going to. Now, Think back to Algebra 1. What did you do a ton of in Algebra 1? To the point where you got sick and tired of hearing about? What was it? Yeah, slope-intercept form. Look at that. Atta boy. Ah, that's right. Now, what would happen if the slope was 0? What would happen if your slope was 0? If m is 0, what do you have? So you get y equals b. And what does that look like? It's just horizontal line. That's right. Exactly right. That is what we call a constant. This is a constant. All right? And so if this were true, then if m, let's think about some things here. Let's call this slope, let's say that m is our acceleration. Why would we say that? Well, by definition, acceleration is a change. It's a change in velocity, and in this case, just speed over time. Isn't that the very definition of slope? Change in something over change in something else? Change in y over change in x, yes? Now, I don't know about you, V, but if it's me, dear, I think I'm going to take this equation up here for a moment, and I think I'm going to write it thusly instead. Is that cool with you? Huh? Mr. Grimm, what's B? It's a good question. This is clearly some velocity. It is, if you will, an added velocity, right? That's how much we've added, right? Every second we're going to be adding more velocity, yes? So we're adding velocity. What are you adding the velocity to? Well, I mean, it wouldn't make sense to add velocity to apples, would it? Let's add velocity to cats. That's weird. I feel like you'd add velocity to, I don't know, velocity, right? I mean, I have some velocity, and I'm going to add some more, yes? So we're going to add this to some other velocity. Now, that looks weird, because there's like v's on both sides. Is this v here the same v as this v over here? No. What would you call this one over here?
V1.
V1, because maybe it's the initial?
Yeah.
Like, well, maybe we call it V sub O. Your book uses O for original. Some books use I. But initial. What would you call this guy? Final. Nice. Nice. And this little formula right here is literally just y equals mx plus b, isn't it? That's it. Wait a minute, though. Wait, that feels weird. So it feels like if I have constant acceleration, it's going to look something like this, isn't it? Yeah? That is, I had some initial velocity. This is my v sub o. And if I let it go for some t units, some t amount of time, I will add added velocity. And where will I end up? I will end up at v sub f, yes? Right. I don't like memorizing it this way. I like that for a demonstration because a lot of kids are like, oh yeah, y equals mx plus b. We did that all the time. I don't know about in Spain, but in America we beat the crap out of y equals mx plus b. Do you do this a lot? Do you just do you see this formula or something like it all day? To the point where you're sick of looking at it? Well, good. This is good. Once in a while, it comes to benefit us, yes? Once in a while. Now, me personally, Mr. Cross, I'm lazy, sir. I want to solve for A out of this mess, if you don't mind. How would I solve for A up here? How would I get A by itself out of this guy? Wouldn't you minus V sub O to both sides? And then divide by T? Look at that formula right there. You know what this looks like to me? It looks like a change in velocity over time. That is literally the definition of acceleration. This is your very first formula you will learn this year, right here. This guy right here. I will just refer to it as the definition of acceleration, because that's what it is. Notice that you're not memorizing a formula. You're memorizing something that's a relationship. right? Acceleration is change in velocity over time. That's it. That's number one. Notice the different ways that it can come into play. This one will show up frequently. Could you solve for V sub O? I guess. That's why you took algebra 2. Could you solve for T? I suppose. But could you do that from right down here just as easily? Yeah, exactly right. So I just memorized just this guy right here. Because to me, it's just so much easier. How about you? Not bad, huh? Is that good for you? Now, yesterday we mentioned it briefly, and I'm going to write it again. Except I'm going to add that little V on top. This little V just means average velocity. Earlier I told you, I'm going to tell you it's 300 miles to my dad's. Well, I told you that. But I was talking about going there and back, yes? One time, I remember years ago, when the kids were little, still in diapers. I remember they were still in diapers because we get out the driveway, I back out on the street, and maybe halfway down the block, and she's like, "Did you grab the diaper bag?" And I went, "No." So I pulled down the street, and I'm back to the house. And I'm at the house for a couple of minutes, in park, obviously, as I run in and grab the diaper bag and whatever else. Honest to God, this truly happened. I get down the street a little further this next time. Do you remember to turn the whatever on? No. This time I was like just about at the edge of Scappoose, so not too far, but far enough it was annoying. Did you remember that? No. 4 times I started to leave the house. 4 times we had to go back. Did it really take you 2.5 hours to do that? Because that's what it looks like on the paper here, yes? No, it didn't take me 2.5 hours, yes? But I'm exaggerating just a skosh, right? It took, oh my God, we're so late. We were late leaving anyways, and then we wasted another half an hour dinkle farting around, okay? Then, Mr. Goom put his foot down, and then somebody had a smelly diaper. So, right? And then it was, feed the kid, and we still got there in 5 hours. Nice. What was the average velocity of the trip? The average velocity of the trip. That is from start to finish, which was 300 miles away, yes? This is where I started, this is where I ended. What was the average velocity across there? The average velocity is what? It's 60, right? I can do math, yes? It's 60 miles per hour. However, what can you say about right here? Mr. Groom, you were hauling some serious butt. Yes, I was. Mr. Groom, what were you doing here? Well, I already told you I was changing the diapers, so what were we doing? Stopped very briefly, yes? And this one is probably a little longer because it was feeding the kid. It takes a little longer, I don't know, but whatever. Mr. Groom, what were you doing here? What happened here? Notice I just went out there and did this. Was I stopped just briefly right there? I was probably flipping a U-turn, yes, but in the middle of my U-turn, what was I? Was I gaining any more distance from home right there at the end of that baby? And then what did I start doing? I started coming backwards, yes? If a person were doing this, was Mr. Groom, okay, here's my average velocity. It's from there to there, yes? The slope of this line, is 60 miles per hour, yes? But what can you say about here? It's a lot more than 60. It's probably 120. I was not doing 120. Okay, I've never went 120. I've never gone over 100 with my kids in the car. That's a true story. I haven't been 100 in a few years, actually. It's been quite a few. Years ago in my Nova, I would do 100 frequently, but not for a long time. I'm a smarter man now. What kind of velocity did I have right here? What kind of velocity do we have right in here? Positive or negative? Negative. Why? Because the slopes are. Okay, this is a positive slope right here. Positive slope. Positive slope. What kind of slope do you have here? Negative slope, which means negative velocity, right? Exactly. And again, what kind of slope did you have here, here, at the very tippity top here, the very tippity top here, when I was sitting at the house grabbing a diaper bag? What kind of slopes did we have there? What? Say it?
Neutral?
I wouldn't say, well, okay, I was in park. But I was looking for a number, sir. I'm looking for a number. How fast was I going? 0, that's right, right? When you are parked, you're not moving, yes? At these points right here, my displacement was not changing, yes? So I had 0 slope, right? By the way, Mr. Whoever's class that taught you that, if you have a horizontal line, what is the slope of a horizontal line? 0. That's exactly right. That's why we learned these things back in the day, okay? Now, this guy here, we can actually look at. We can have some fun with. It's a good time. We can't do any real math with it. Now, when you say, Mr. Groom, x equals v bar t, how did I do that? Well, I took the average over that region, yes? The average over that region was 60 miles per hour. Okay? Now, again, everything we do in this class, we will be assuming constant velocities, or constant accelerations, I'm sorry, constant accelerations. That's everything we do in this class mathematically will be assuming constant accelerations. So if I told you that initially we were going 10 meters a second, and later on, sometime later on, we were doing 30 meters a second, and you are assuming constant acceleration, what was your average velocity over that interval? Okay, it's really easy. I made it really easy. What's the average of 10 and 30? Nice. And so when you want to find this guy, it is simply the average of these two. And this is, again, assuming constant acceleration. Okay, but this right here, this is your second. You hippie. This guy right here is your second formula that you probably should have memorized somewhere. Okay? Mr. Groom, what if my acceleration was equal to 0? Well, is that constant? Feel like it is. So if there's no acceleration, baby, that's your formula right there. Okay? That's formula number 2. Okay? Formula number 3 is one of my favorites. Here's a question for you. Here is velocity. Here is time. Here is 60. Mr. Grimm, you sure hit 60 a lot. That's right. I don't like to speed. That's not true. I do like to go a little bit. Not enough to speed. I don't like to speed enough to get caught and get a ticket. That's annoying. But I like to speed just a little bit. By the way, I passed Mr. Young this year. The dude drives like a little old lady. Seriously. I'm like, what are you doing, Corey? What is going on? I like honking, waving at him, and he's like, it was like 6:30 in the morning. He's just like, yeah, with like 40 miles an hour and like a 50. I'm like, what are you, let's go. How far did this person travel in these 5 hours? How much? How much? 300 miles. Like, Mr. Grimm, you keep doing the same thing. I know. What does 300 mean to you when you see this picture? If I just got rid of this, and this, and this, and this, what does 300 mean to you? Say it. What? No. If all you saw was this picture, it was 60 on that side and 5 right here, and 300 would mean what to you? The area. That's right. That's right. It's area, is it not? It's area. Am I right? Am I right? I feel like I'm right. Now, let me draw these back on. The area in here, the area equates to the displacement. And so the area, we say, under a velocity curve, velocity versus time curve, is displacement. Now, in calculus, we would use a thing called an integral to find area under a curve. But in calculus, we're not going to be finding areas of boxes. They're going to be goofy things like, well, like this. Okay? But the area under a velocity versus time graph will always be displacement. Always. And so you're like, well, let's do just v times t. In this case, it gives me the area of a box. That's exciting. It's not very exciting. But, Taylor, is it Taylor? Yes, I've got one kid memorized. This is one new kid memorized. This is exciting. Nice. Steve. No, God. See, I quit. Bird Sal. Jacob.
Yeah.
That's kind of cheating, 'cause I think I know your parents, right? But whatever. It's kind of cheating. But whatever. Hey, whatever. And I know that Pablo Antonio over here, but Pablo then Antonio? God dang it! I suck so bad with names.
My name.
That's guy had you last year.
That's because your name's Avery.
I swear.
Avery?
My cousin neighbor got one.
Oh, no, that's weird. Okay, so I want to... Here we go. But listen, suppose I were to do this, dear. Are you good with me drawing this line right here? V and T, is that cool? Is that cool? All right. Taylor, I'm going to ask you this question. Taylor, suppose this person started off at 10 meters per second. And let's suppose that, I don't know, 14 seconds later, the person is now going, I'm just going to make one up, 50 meters a second. Could you, Taylor, find the area under this curve? Is it possible for you to tell me that? Because we have just said that the area under curve is displacement. Okay. How would you find the area under this curve? What is that curve called? What is that shape called? By God, it is a trapezoid. That's right. Nice work, kid. And how do you find the area of a trapezoid? Flashback to 5th grade or something, right? What?
Side 1, my side 2, my side 1.
Plus side 1. But yeah, I got you. So I always remember it as base 1 plus base 2 divided by 2, right? When you add two things together and divide by 2, what are you really doing? You're finding the average base, yes? All right, and then what do you want to do after that? Times it by the height. Yeah, good job. Good job. Thanks for your help, Alex. That's good. Good. Now, times it by height. That's right. Exactly right. Now, who would your bases be in this particular problem? Okay, then. We'll go back to you. Who would the bases be in this problem?
10 meters.
These fellas, yes? Nice work. Nice. And so if you were to find the average, I feel like that would kind of be where it would be, yes? And this little part right here, you could slap it into right there, right? And in essence, you'd be creating yourself a rectangle, yes? That's nice. But wait, there's more. Now, dear, what would you call this 10 on this side? What would you call it? That's what happened at t equals 0. So what would you call it? You'd call it a v of some sort, but v, the original v, yes? V sub O? I like it. Plus, what would you call this one over here? V final, beautiful. Divide by 2. Wait, I think we have that formula somewhere, don't we? And what would you call this h? What would h be for us? It's not really height. What's down here on this axis down here? Time. That's right. That's right. That's right. Wait a minute. Mr. Groom, isn't this just v bar times t? I would argue it is v bar times t, isn't it? Yes? It's an average velocity times time. That's nice. Now you're like, why would you tell us that? Well, because I'm building to something. I promise. I promise. It's as if this person had gone 20 meters a second for 14 seconds. This person went 280 meters, yes? Right? 20 is the average times 14, 280 meters. You with me on this? All right, but there's more. And we're going to finish off with this. Let Mr. Groom make a little substitution if you don't mind. I'm going to pull this 1/2 out front. That's aight. If it's not, I don't care. I'm going to do it anyways. Okay? Plus. Now, do you recall on the previous page or two we wrote this little fella down? Oops, we didn't write that. We wrote it this way. Remember writing that down? I'm going to make the substitution right here if that's okay with you. Okay? I'm going to replace V sub F with this guy. I'm going to write it like this for no apparent reason right now. Times time. That cool? So how many v sub o's do we have in here? Well, we have 2 of them. That's right, we do. You're right. Hey, now let's distribute. Bloop, 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 bloop. And when you do that, you should get v sub o times t plus 1/2 at squared. Is that true? It is, I promise. I'm not going to lie to you. That's true. That formula, back in the day, it was not hard for me, but it was like a lot harder for me to put that together for kids back in the day. I don't know why. Was I stupid? Maybe. I don't know. Whatever. It was just harder. It didn't come off my tongue as easy. But this formula right here, friends, and I usually write it this way. And Mr. Groom will often write a little X and naught because I might not always start at 0, yes? Like if St. Helens is 0 and I'm going to Portland, but I was already at work, let's say in Scappoose, I didn't start at 0. I started at some initial displacement, if you will. Okay. By the way, could this guy be 0? It could be. It could be, but it doesn't always have to be. This guy right here is formula number 3. This is what I like to refer to as the grand poobah. It is the big one. Poobah, the grand poobah, if you're not familiar with Flintstone characters back in the day, Fred Flintstone belonged to the Moose Lodge. The Moose Lodge. And he was the grand poobah at the Moose Lodge one year. Okay, it was a big deal. Back in my childhood, it stayed with me over the years. It's the head mucky muck. It is the big one. Check it out. This is pretty exciting. Watch what happens. Watch what happens if there's no acceleration. Shut up. X equals vt? What? Isn't that cool? Yeah. Does this formula kind of encompass all the rest of the ones we've been dealing with? Sure does. And it's a pretty slick deal. Okay? This guy here we will use a ton. We will change it just ever so slightly when we drop things, because instead of going in the X direction, we'll go in the Y direction. And when you drop things, it's not just any old A, it's actually gravity, yes? So we'll keep those things in mind as we're doing these problems. But this formula here, which I again will refer to as the grand poobah, because it doesn't really have a name. That's what I call it. This is one of our formulas. So today, you've got 3 formulas. You've got this guy, you've got this guy, and you've got, what's the other one? The definition of acceleration. These 3. Now tomorrow we will... Why did I write over 2? That's dumb. Sorry, let's try that again, Mr. Groom. Over T. Someone might readily ask, but didn't we learn this one too? We did. I feel like that's just the definition of an average, so I don't really know if you need to write that down. Okay? But these 3 guys right here, tomorrow we'll learn our last one, and then we'll start doing some example problems and talking about some more about this. Notice that nothing we did today was higher than Algebra 1 level, right? Okay, we found the equation of a line. Whoop-de-doo. By the way, if you graph this one, what does it look like? That's a parabola. That's right. That is why we study parabolas and linear functions a ton, because it has to do with what we see in physics all the time. Okay, it's one of those things. Remember that all the math that we teach you pretty much in high school on is preparing you to be an engineer. It's sad, even though you personally might become a cosmetologist or a I don't even know, a logger, I don't know. But you're educated as if you're going to become a physicist or a engineer. Mr. Groom, when will I ever need to do logarithms? I don't know, what are you going to be? Mr. Groom, I am going to be a janitor. Then never. However, it might interest you to know that the half-life of the smell of onions in the kitchen does decay exponentially. And you can use logarithms to find out when it will be below a certain level. I don't know that I would do that, but it's nice knowledge to know. Okay? Or if someone's been in the bathroom ahead of you, like your brother, and in half an hour it'll be safe to go in there. Okay? It is exponential decay. You can use logarithms to figure those things out. In my day, it was always about, what if you accidentally spilled some plutonium here? When could you live here again? Never. Well, the half-life of plutonium is 32,000 years, give or take. So, never. Well, when could your grandkids? Ooh, trick question. I don't have any kids. And if there's plutonium and I'm right here, I'm never going to have kids. So my grandkids, moot point. Oh, come on, do the math. I don't want to do the math. That's a stupid question. If you'd have phrased it in, when would it be safe to get in the bathroom after your brother? Oh, I can do that one. And that actually makes sense. Okay, I don't accidentally spill plutonium very often.
Well, you don't.
No. Although we used to live downwind from Hanford, so that was a big deal. What if Hanford blew up? Well, what if it did, friend?